Hey everyone, in this video we're going to be going through some passages and then answering the questions related to them. And I scored in the 99th percentile on the MCAT, so with this video I'm trying to show you how I would look at a passage, look at what information matters and what doesn't, and how I would break down the passage, and then how I approach all the questions, how I see what the question is asking me, and then go through all the answer options, see what's correct, what's incorrect, eliminate them one by one until I have the final correct answer. So hopefully me going through these passages will show you a right approach or like the approach that I used, and if you apply these techniques that should help you increase your score as well. Of course, if you have any additional questions, leave them in the comments below, but as I go through all these questions I won't assume that you know too much background knowledge. Like, of course, I'll assume you have done some studying for the MCAT, but all the information that you need for a question, what is present in the passage, I'll try to show you where it is and how you can use that information to answer the questions. So without any further delay, let's get through the passages. Next, we're going to be looking at this passage, which is mainly focused on dipoles and electronegativity. So this passage says that many chemical bonds are not purely ionic or covalent, but polar covalent. For example, in an HCl bond, chlorine, it has a greater attraction for electrons than hydrogen does, and therefore it develops a partial negative charge with respect to the hydrogen atom. So this is stuff you should have already known, what an ionic or covalent bond is, and then covalent polar and nonpolar. And because the chlorine is more electronegative, it is hogging more of the electrons. Even though it is a covalent bond, they spend more time around the chlorine, and that leads to a dipole. If the partial charges are separated by a known distance, then the dipole moment, which is a measure of the charge separation in a bond or molecule, can be calculated by the following equation, where the dipole moment is just the charge that we have times the separation distance, so multiplied by that. And dipole moments are usually measured in debye's, or that D, capital D, where 1 D is equal to 3.34 times 10 to the exponent negative 30 coulomb meters. So that's just about dipole moments. And then finally, they tell us that the molecular geometry of some simple molecules can be determined based on the presence or absence of a net dipole moment in the molecule. The observed molecular dipole moments of various compounds are reported in Table 1. So that's another important thing that you should know regarding dipole moments, and the MCAT definitely, like the AAMC, they have enough questions about this that they do want you to care about it. If we have some compounds where the geometry in 3D space is symmetrical, then even if there are dipole moments individually in some bonds, the overall molecule may not be polar itself, because all the net dipole moments, they cancel out. And I can give you like a quick example of that, I guess. This is carbon dioxide. Between the carbon and the oxygen, there's a difference in electronegativities. So like there might be a dipole moment going this way and another dipole moment going this way, but since the molecule itself is linear, these are like at 180-degree angles from each other. These bonds, their magnitude is the same, the dipole moments, the magnitude is the same, so they cancel out, going left and right. Overall, this is not a polar molecule. And then let's get to this table. Table 1 showing us dipole moments for various compounds. First column shows you a compound, second column shows you the dipole moment. We don't have to worry about this too much with any like chemistry related passage. I don't really care about the data inside the table. I just understand what's in the table, and then if I need it for a question, I'll go back to it later. So that's just table 1. Getting into the questions, question 17 is asking us, which of the following best explains the observed molecular dipole moment of this compound, tin tetrabromide? So in this case, we go back to this table, we see that that compound has a 0 dipole moment. So they gave us this data, this compound doesn't have an overall dipole moment. What explains that? So right at the end of the passage, they reminded you that the geometry might lead to compounds not having a dipole moment. If you just record whether they have a dipole moment or not, then that can maybe tell you something about the geometry. So the fact that this doesn't have any dipole moment, that leads me to the immediate conclusion that the molecule is symmetrical, and because of that, the dipole moments cancel out. And if I just pull up the periodic table, and of course for these questions, you'll have the periodic table on the MCAT. It's up to you to memorize more specifics about the periodic table, but you can see that, I don't know where'd it go, here it is, tin is down here. It's in the same group as carbon. So that is going to react similarly, or it's going to have a similar geometry to how carbon would have if it was bonded to 4 things. So that means, like, think of methane, CH4, or carbon bonded to 4 things. It's going to be tetrahedral. So we'll have 2 bonds like that, and then just like it's tetrahedral. It's like that. 2 in the plane, 1 coming out at you. Not the best drawing, but you get what I'm saying. This is a tetrahedral molecule, 1 going away. Because of that, like, the 3 at the bottom are kind of going out in equal directions. They cause a net dipole moment going downwards, and then there's a dipole moment from this one going upwards, and the downwards and the upwards, they cancel out. This is a symmetrical molecule, something that's tetrahedral. If all the things it's bonded to are the same, so each of these individual tin bromide bonds has a dipole moment, since they're all the same, they all cancel out in the symmetric molecule, and there's no net dipole for the compound. If you swap 1 or 2 of them, depending on like where you swap them, if like the top one became like hydrogen or something, now you do have a net dipole moment because it's going downwards and there's nothing canceling it out upwards. But in this case, the symmetry is why we see no dipole moment. So let's look at the answer options. A is saying tin and bromide have the same effective nuclear charge. No, that's not what's going on. So effective nuclear charge, that is saying the valence electrons, the ones in the outermost shell, and those are the ones which are the most important for chemical reactions, those electrons, how much of the charge, the positive charge from the nucleus, do they actually feel? Because there are other layers of electrons in between them that are shielding them from that charge. So the effective nuclear charge is the charge from the nucleus, subtract how much is shielded by other electrons in between, and then how much the valence electrons actually feel. That's the effective nuclear charge. And that's a similar thing to saying that, like, those valence electrons, the effective nuclear charge they feel, that's a similar thing to saying that they have similar electronegativities. But the tin and the bromide definitely do not. So just to remind you, electronegativity, if we're using the Pauling scale and we're looking at this periodic table, let me just erase this. The fluorine over here has the highest, and then other things that are closest to it, they have high electronegativity as well. As you go this way towards fluorine, electronegativity increases, but tin is over here, and then bromide is over here. Bromide would have higher electronegativity, it's closer to fluorine, and it's going to pull electrons towards itself. So option A is incorrect. It's implying that they have similar electronegativities. That's incorrect. Option B is saying that they're the same size, but we're more so worried about electronegativity than size here. Not really clear how size would play a part in the dipole moment. C is saying tin attracts electrons more strongly than predicted by its electronegativity. No, like, even if it did, then that would mean that there's a net dipole moment in the bond itself. So why isn't there one for the overall compound? But C is an incorrect thing anyway, because bromide, or the bromine, is more electronegative than tin. But D is actually hitting at what's correct here. It's the geometry of the molecule which causes the bond dipole moments to cancel. Overall, there's no net dipole. So D is the correct answer here. Moving on to question 18. Which of the following figures most accurately depicts the sigma bond, or the sigma electron cloud, in the nitrogen oxide molecule? So in this case, we're talking about a molecular orbital that has formed by overlapping the s orbitals, the 2 s orbitals from nitrogen and oxygen, and we have the sigma orbital which is formed. So a molecular orbital is just an electron cloud, giving us the probability that an electron will be at a certain point. And if these 2 things are bonded, then there isn't going to be a gap here. Like, it makes no sense that there's a gap between them in option A. That's incorrect, because, like, there isn't a node there. Sigma, or like an s orbital, is, like, if this is the nucleus, it's a circle around a nucleus. It'd be a circle. There's no node in between, so that doesn't make sense. There would still, we would expect electrons to be in between the nitrogen and oxygen, and that's the main point. Like, the nitrogen and oxygen are trying to share electron density. They're forming a bond for that reason. So it's not option A. So what you do expect is a bond between them. So you see an orbital showing that there's electron density between them, but because of electronegativity, if you just go back down here to the periodic table, you see that oxygen, which you see right here, is closer to fluorine than nitrogen, so oxygen is more electronegative. That means that there's going to be more electrons like around oxygen. They spend more time around oxygen, it's better at pulling them towards it. So B is incorrect because it's implying that there isn't like polarity to this bond and that it's equal. That's incorrect. C is incorrect because it's showing them more so around nitrogen, but that's backwards. They should be more so around oxygen, so D is the correct answer. Question 19 is saying, based on the observed dipole moment of hydrogen fluoride in table 1, what is the observed dipole moment for hydrogen chloride? So look at HF, tell me for HCl, and then in this table we don't actually have HCl, we just have HF. So when I look at HF, I see that the dipole moment is 1.82. Okay, and then between that and HCl, the only thing different is the Cl. I said fluorine is the highest, right? It's the most electronegative. So what is happening now? We are changing from fluorine and we're going to chlorine, which is right here. It's very close to fluorine, so it is very electronegative, but it's less electronegative than fluorine. So if in HF my dipole moment, because of the pole of the fluorine, was 1.82, now the pole is smaller, so that charge that we have, that's going to be smaller. I expect still a dipole moment to be there, and it should be like, reasonably strong, a similar strength to HF, but it's going to be less because Cl is less electronegative. So something close to 1.82, but less than that. And option A is just way too small. It's implying that there's almost no dipole moment, but that doesn't make sense because chloride is still a pretty electronegative element. B makes sense. It's less than the 1.8 number that we saw with HF, but still there's a dipole moment. And then C and D make no sense. There's no way that the dipole moment would increase. So that's B. We can just make that guess. You just have to just look at trends in electronegativity and then think of the difference between the F and the Cl. Question 20. Which of the following best explains why HCl bonds are polar covalent? So the passage told us HCl is a polar covalent compound, and like a lot of people think HCl is ionic, but it's not ionic. It displays more covalent characteristics than ionic characteristics, even though in an aqueous solution it does dissociate into like H plus and Cl minus. But the passage straight up told you this is a polar covalent compound. So why is it polar covalent? There is a covalent bond between the two, but it's polar because there's an electronegativity difference. So one of them is hogging the electrons more, and so the straight up answer is that the chlorine is more electronegative than the hydrogen. Because of that, there's polarity to the bond. So that's the answer option we're looking for. Option A is saying hydrogen atoms are smaller than chlorine atoms. While that is a true statement, that doesn't explain why the bond is a polar bond. Electronegativity is a trend that we're looking at in this case. That's a relevant trend. Option B is implying that H atoms are more electronegative than chlorine atoms. Definitely not. Chlorine is right by fluorine. It's a very electronegative atom. Hydrogen is not as electronegative, or definitely not more electronegative. It's the opposite. Chlorine is more electronegative than hydrogen. Option C, also pretty crazy. It's saying that they have equal electronegativities. First of all, definitely no. And second of all, if they did have equal electronegativities, then this compound would not have polarity to it. It would be non-polar covalent. So that leaves us with option D, and it is a bit of a strange sounding option. It's saying chlorine atoms have a greater effective nuclear charge than H atoms do, and I explained this in a previous question. Effective nuclear charge is just the valence electrons. How much of the charge from the nucleus do they actually feel when you take into account how much of the charge is shielded by inner electrons? And that is implying that, okay, if there's a great effective nuclear charge, that's saying like there's a great amount of pull that the nucleus has on electrons, and the pull on electrons is a similar term to just talking about electronegativity. So this is just saying that chlorine is better at pulling those electrons towards itself, so it's more electronegative than hydrogen. It is a roundabout way of saying what the thing is that you should be thinking in your head, but you can remove the other answer options and also figure out that this strange wording that they have here is just talking about a concept that you were looking for in the first place. They're just kind of trying to make you doubt yourself a little, I guess. But D is the correct answer. And just as a note, I have seen that happen a few times, and I've seen it on my own MCAT, and there were a lot of times where I thought, like, this is definitely the correct answer, but I read it again and again, and I'm like, is this saying what I think it's saying? Because if it's not, then I'm choosing the incorrect answer. But, you know, through the process of eliminating the other answers and being pretty confident that, yes, I am kind of transcribing this or like translating this sentence properly, then yeah, you can figure out that that is the correct answer. So D is the correct answer here. Watch out for that on your actual MCAT. And we're going to move on now to question 21. If an oxygen atom is removed from carbon dioxide, the observed molecular dipole moment will what? Will it increase? Will it decrease? So we took oxygen, we removed it from carbon dioxide. So that was the example that I gave before. I have this compound. It's a linear shape when we think about its geometry. So even if there is a dipole moment going this way, they cancel out with each other. But now, if I have one of them removed and say I have this compound, still a linear compound, but now I have the dipole moment just going one way, and there isn't something to cancel out the dipole moment the other way. So if nothing's canceling it out, there's a net dipole moment now with the carbon monoxide that wasn't there in the carbon dioxide. So comparing the two, the first did not have a dipole moment, the second one does, so the dipole moment will increase. So option A and B are saying that it will decrease. That's incorrect. A is saying it's going to decrease because a lone pair of electrons will be formed on the carbon. I mean, no, that's not what's going to happen. If you remove an oxygen, it's going to turn into carbon monoxide. And either way, even if it was like a lone pair, that doesn't mean that now there's like some other dipole moment that is present and is canceling out the dipole moment that's there on the other side. Like electrons, they play a role in geometry, but not so much dipole moment. Dipole moment is more so electronegativity that we're focused on. Option B is saying it's going to decrease because the net charge will increase. If the net charge increases, like why would the dipole moment decrease? And either way, in these compounds, if we're talking about like charge, there isn't really a charge. Carbon dioxide doesn't have a charge. Carbon monoxide doesn't have a charge. No. Usually when you see, like the classic examples are like carbon in a tetrahedral form, like CBr4, or carbon dioxide. You see these classic examples given to you when you're learning about dipole moments to show you that these compounds, because they're symmetrical, their geometry is playing an important role here, and now there is no net dipole moment. So, like, if I ever see a question like this, talking about dipole moments and carbon dioxide, it is telling me that, you know, this is a compound that usually had no net dipole moment, so something is going on here relating to that. Option C is saying it's going to remain constant because the geometry will not change. No, well, the geometry technically is still linear, but what matters is there isn't something canceling out the dipole moment. So, you know, it is true that it's saying, but it's not the whole picture. D is the correct answer. It's going to increase because a charge separation will develop. This should be the final question. Which of the two compounds, PCl3 or PCl5, can be expected to have a larger dipole moment? So there's like a lone pair over here on PCl3. This is a trigonal pyramidal compound. Option A is saying PCl3 has a larger dipole moment because it's trigonal planar. So first of all, the planar part is incorrect. The lone pair means that it's not planar if you have three things bonded and then the lone pair is trigonal pyramidal. So option A is incorrect. And option C is also incorrect. It's saying that PCl5 is octahedral. It's not. It's trigonal bipyramidal. When you have the central thing with 5 things bonded around it, it's trigonal bipyramidal. And 6 things are bonded when you have an octahedral geometry. So because of those reasons, we remove options A and C. Now we get into the actual question. Which one has a larger dipole moment? With PCl5 over here on the right, these 3 are in the same plane and they're symmetrical, like 120 degrees from each other. So these guys, even if there is like a net dipole, it's canceling out. So within that plane, those 3 things are canceling out. Just like if you had something which was trigonal planar, that also would be symmetrical, and in its plane it would cancel out. And then we have things going up and down, like all of these dipole moments, they're canceling out. Trigonal bipyramidal molecules are symmetrical all around, so that's all going to cancel out, no net dipole. So the one with the larger dipole moment is going to be PCl3, and yes, its geometry is pyramidal, not option A, which is saying trigonal planar. So with this guy, you see, like, this isn't exactly a plane. It's kind of bent downwards, right? So that means that there's a net downwards dipole moment. If there was something up here to cancel that out, then, there would be no net dipole, but there isn't. So there's a net dipole moment going downwards. So PCl3 is the one that actually has a dipole moment, and the correct geometry is pyramidal. So, if you're lost on this type of question, make sure you do a lot of Vesper question examples so that whenever I have central atom with this many things around it, this many lone pairs, this is its molecular geometry. And then if you understand that and you understand symmetry and dipole moments canceling out, then you can answer this question. And that is the last question for this passage. If you look down in the description, you will see that we have a course, right? We have a 30-day MCAT course. All the information for that is down below. You can check out our website. We also have like a webinar that plays from time to time, and it can give you more details on what is in the course. But essentially, what you saw here is what is going to be present in the course. We have lecture videos going through all the different topics that are covered on the MCAT and explaining those topics to you, but like at the level that you need to know for the MCAT. We don't try to go like way too beyond, because you don't have to for the MCAT. And then a lot of videos for like over 1,000 questions, going through the questions, going through the answers, breaking it down like you saw here, and then trying to teach you this method of approaching questions critically as well. So if you like what you saw, make sure to check out the link and see if this course is right for you. We call it 30-day MCAT course. You don't have to only be willing to study for 30 days to take this course. We have schedules for 30 days, but also for 60 days, for 90 days, or just however long you need to study. So you can just get in the course, you can move along at your own pace. The main thing is, if you like what you saw in this video, then check out our course. And that is it for this video. I'm going to end it off here. If you have any more questions, reach out to us, social media, email, everything like that. So thanks for watching. See you guys in the next